See students, as per the syllabus, we need to discuss the position of transition metals in periodic table, and about which we had a sizable discussion, not a too long and too short discussion, sufficient discussion we had. What is natural occurrence, principal ores and minerals or different transition series elements, different ores are there, but we have not discussed this point. I am keeping this point for you as a work. Later on we will sum up with all the points. Those you need to prepare, you need to work for that. It is just the mainly memory based task, but this point we discuss significance of spatial stability of D0, D5 and D10 leading to variable oxidation states. It is better that we should have the revision, because follow-up session is our the decision. Will anyone inform the first point? Where are these transition series elements situated or positioned in the periodic table?
between S block and P block element.
Yes, it remains general explanation, but if you would say those are in group 3 to group 12, group 3 to group 12 means it indicates that it is after group 2, which involves the so-called S block element, and it is before group 13 means those are so-called P block element. I said already, saying S, P, D, F as a block, still in many books those things are used, but I intentionally avoided to use them. If you go through the Concise Inorganic Chemistry by J.D. Lee, one of the path-breaking book, there you will find these are called transition series element, transition metals. Otherwise, in your syllabus also they would have mentioned D block metals. So S, P, D and F, these nomenclature, though conventionally we are following, or you will find in the several books, we are avoiding to mention S and P. What will we say rather than that? We will mention group number. We can mention the period numbers. So just as said, these transition series elements are from group 3 to group 12. But here answer doesn't complete. What we need to do, we need to specify period number. Will anyone answer what are the period numbers for transition series metals?
4.
4, 5. 4 is first transition series. 5th period is a second transition series, which starts from yttrium. First transition series starts from scandium. Third transition series starts from lanthanum. And last, fourth transition series starts from actinium. So once you mention the period number and the group number, there itself position becomes very clear. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Next point is significance of spatial stability of D0, D5 and D10. Will anyone answer what general concept we carry about this electronic configuration? Why are these stable? Why these electronic configuration we consider as a stable electronic configuration? What is the specialty of D0, D5 and D10?
It is a half filled electron orbital.
Yeah, it's about D5 you can say half filled. What about D0?
Governor extra stability.
Yes, that is mentioned in the syllabus. Spatial stability. We are agreeing to that. They govern extra stability. They are with spatial stability. I want a description for D0, D5 and D10. What D0? Half filled is only for D5. My point of question is explanation of all D0, D5 and D10. How are these electronic configuration? They are stable. Spatial stability is there. Okay, all those points are there. But how do we describe this D0, D5 and D10? Just I got one answer, but that was only for D5. I want the description for D0 as well as for D10.
Empty and fulfilled.
Right. D0 empty d orbitals, D5 half filled d orbitals, D10 filled d orbitals. These are the stages you can see. These are the steps you can understand. Vacant orbital means orbital yet not started to fill. Means it's like a boat. Nobody is there in the boat. Okay, equilibrium. 50% occupancy, but in one particular manner, window seats only, equilibrium way, because 5d orbitals are there. Central orbital we consider as a zero from third quantum number or magnetic quantum number point of view. The first orbital if I consider plus 2, last orbital will be minus 2. Second orbital if I consider plus 1, second last orbital will be minus 1. So plus 2, plus 1, 0, minus 1, minus 2. These are the magnetic quantum numbers for d orbitals. And if I consider d5 electronic configuration, following Hund's rule of maximum multiplicity, each orbital will be with unpaired electron. So plus 2 will cancel minus 2, plus 1 will cancel minus 1, and 0 is there. Nobody need to cancel that 0. So total magnetic momentum, if you see, it will be 0 for D5. Certainly it was for D0 also. So it is one kind of the stable electronic configuration because there is one kind of symmetry. There is one kind of particular arrangement. There is no net magnetic moment. There is no net third quantum number. You can say magnetic momentum. Therefore, D5 also is stable. In case of D, if p orbital would have been there, then in spite of D5, here D5 is there, then for p, what will be electronic configuration? Half filled. For d orbital, 5 is a half filled electronic configuration. Then for p orbital, which will be the half filled electronic configuration?
3,
Right, 3, p3. For f orbital,
7,
right, of course, they are in each window, of course, they're in each sub level, or can say orbital. One electron will be there, unfilled electron will be there, causing net magnetic momentum 0. So for D0, completely vacant, D5, half filled, and D10, you will easily understand. D10 means completely filled. But why completely filled orbital governs extra stability? Because magnetic momentum, net magnetic momentum is 0. Yes, could you able to understand for D10 net magnetic momentum is 0?
Yes, sir.
At least one more answer.
Yes, sir.
Yes, sir.
Okay, good. Good. Now I want your help. What is the example for D0? I want example for D0. Which ion will you furnish for D0? Say if I take scandium. Yeah, scandium. What should be charge on scandium? What should be charge on scandium so that D0 configuration will be there? Yes, somebody said
Plus 3. 3.
right. Plus 3. Plus 3. Bear with me because today I'm not with that the writing pad and the pen. Okay. Second, for D5, I want example. What's the example for D5?
Fe3.
Fe3. Is it right? Other students, whatever the answer that I got, Fe3, is it right? Hint I told to you, find atomic number for dipositive, last digit. For tripositive, less than that. What's the atomic number of iron?
26.
26.
26. So 6d6 will be the configuration for what? Fe plus 2. For Fe plus 3? Absolutely. Answer is right. That is what d5 configuration. Therefore, what we say? Ferric ions are more stable than ferrous. And reason is the spatial stability of half-filled d5 orbitals. Very good answer. Very good answer. But I want one more example. And hint I give it to you, that ion, that metal ion is a dipositive, not tripositive. Dipositive metal ion from first transition series, and there is a D5 configuration. What is the example?
Manganese.
Yes, very brilliant answer. Yes, answer is manganese. Just now, Mn plus 2 I'm talking about. Okay, now last, for D10 electronic configuration, which example will you give?
Copper.
Charge on that. D10 only copper, but I am asking about the oxidation state. The copper is stable, but not to the great extent. Silver,
2 plus.
gold are there. Yeah, charge. Yes, right. Which charge? Plus 1, plus 2.
plus 2.
Think on that. Copper atomic number is
U plus.
right. Cuprous. Copper atomic number is 29. 9 will be there if di positive. D9 configuration will be the di positive. But I want D10. Then which charge should be there? Copper should carry how much charge?
+1.
Right, plus one, we can say as a Q plus, Cu plus. Okay, though on the basis of electronic configuration, we could describe the few oxidation state, still there will be the many oxidation states which we could not describe on the basis of electronic configuration or on the ground of spatial stability. That's a half field, or vacant orbitals are extra stable. It is practically found that these transition series elements show the variable oxygen state. If I take the example for the manganese, then manganese takes values for positive charge, or manganese shows oxidation state right from +2 to +7. Wide variety of oxidation state is there. It is true for other elements also. Therefore, it is concluded transition series elements show variable oxidation states. Will anybody answer what is the reason for that? Ferrous also possible, ferric also possible, Cr plus 3 also possible, Cr plus 6 also possible, Mn plus 2 to Mn plus 7 possible, Cu plus 2 possible, scandium plus 2, scandium plus 3 possible. Possibilities I am saying. What is the reason that these transition series elements show variable oxidation states? Yes, will anybody answer? Let's take example of first transition series elements and just attempt answer. Yes, will anybody answer? If no, then say no. My question is why the case is variability in oxidation state.
No, sir.
Good.
No, sir.
Good. Now let me describe that. Oxidation state is a game of loss or gain of the electron that you know. We are talking about transition metals, and metals are electropositive. Means metals have tendency to give electron, to lose electron or electrons. So they will show positive charge. So they will show positive oxidation state, about which there is no question. Means they are losing electron, they are giving electrons. From which orbitals? Which orbitals have comparable energy? Which orbitals are there who have similar energy? Say, as an example, first transition series. If you help me for this question, you will get the answer. Question is which orbitals are of similar energy, of comparable energy in case of first transition series. Because of that, we find that electronic configuration.
3D, 5U, and 4S.
Okay, 3D and 4s. So d orbital. If I talk about other transition series elements also, then n minus 1d, where n is a principal quantum number for last orbital. If I talk about the first transition series, then principal quantum number is 4. So 3d is a one orbital or one sublevel, and other 4s. So 4s and 3d, they have comparable energy. They have nearly same energy. And whoever are staying in those orbitals means electrons. Number is large, and due to which large variation we find in tendency to lose electron. Large variation we find in their positive oxidation states. I repeat, reason is only one, that just you said the orbitals which are of comparable energies or similar energies are n minus 1d and ns, and those orbitals possesses ample of electrons. Those orbitals do exist more number of electrons, and due to the existence of those more number of electrons, these transition elements show variable oxidation states. Students, are you following what I'm saying?
Yes, sir.
Yes, sir.
Yeah. Now, as a part of revision, you know that this is a new thing. Actually, last time it was not properly revised. Therefore, you are feeling it is like a new thing. But already it is revised that I'm asking now. They are showing variable oxidation state, but there's one formula for minimum oxidation state. What is that formula?
Number of electron in 4s.
Yes, and maximum oxidation state is equal to number of electrons 4s plus number of unpaired electrons in what 3D. And with various examples, you will understand that. Okay, on the basis of electronic configuration, we could describe the stability. as we did for D0, D5, and D10 cases. But there are the several examples where such spatial electronic configuration, spatial stability causing electronic configuration is not there, even though those oxidation states are stable. When which answer can we give for that? Why the oxidation state are stable, or how can we attribute the reason for their stability? How can we describe their stability? So stability of oxidation state, now I want answer from you, depends on three factors. What is the first factor?
Sublimation
Sublimation,
energy.
Yes, it's a sublimation. What's the second?
Ionization.
ionization,
Right. And last,
Lattice,
Solvation.
solve,
solvation or
lattice in
Lattice.
lattice energy. Lattice energy in the solid form, and solvation is in the solution form. Likewise, we could able to describe the various electronic configuration for the ions and the stabilities and overall oxidation state we could describe. That is our point 2.1.2. So here complete. They ask vanadium and chromium. We discussed the several metal ions. Is that point clear?
yes sir.
yes sir.
Yes, sir.
Yes sir.
Okay. Then 2.1.3, origin of color for transition metals and their compounds. Actually, I describe this point to the basic level. Let there be any color or any compound or in nature anywhere, wherever you find a color, there is a reason for the color. And you know that reason. What is the reason? Color is due to
Absorption
Absorption.
of
absorption of electromagnetic radiation in the visible region. Visible for us means for human being, a range of visibility is from 380 nanometer to 760 nanometer. So we say that range is the visible range. It is not perfect 760 or the 380 nanometer. Variation may possible. So from our perspective point of view, the visible range, visible spectrum that we say, and out of that visible spectrum, if anything is removed, mixture will be with some color, or nothing is removed, then it will be white, or everything is removed, then it will be black. So what these things are related to the visible range of the spectrum, electromagnetic spectrum is with wide range. Gamma rays are there, x-rays are there, ultraviolet rays are there, visible rays, infrared, microwave, radio wave, large spectrum is there. Out of that, we are talking about only small region. That's a 380 nanometer to 760 nanometer. And there, because of absorption, color one can see. And that absorption is for excitation of the electron or transition of the electron. And that transition can be for three types. Yes, especially about transitions element. That transition is possible for three ways or three reasons. Yes, what are those? Which types are there? Number one,
D to D.
yes, D to D, number one. Second,
N
Metal
to
tool,
N.
metal to ligand, and last one, ligand to metal. Okay, and these metals are with characteristic shining. All metals are with characteristic shining. Of course, transition says metals are also with characteristic shining. If you see copper, it has color one, and shining also remains different. For zinc, shining remains different. For gold, shining remains different. So I'm not talking about the color of that. I'm talking about reflection. I'm talking about shining. Silver of perfect, different kind of shining. So different metals are with different kind of shining, and to that shining we say as one word called as luster. Those metals show characteristic luster, and that lustrous property could not be described by the points which we still now discuss. We were saying no absorption is there, so DD transition or metal to ligand or ligand to metal transition. Because of luster, we cannot describe. I told one time band theory is there. Band theory means continuous energy levels are there. So electron can move from the one level to the other level and can return to different levels. So while returning also it emits all kinds of lights, all wavelengths. Few where difference may possible, and because of color we find, but because of the too many wavelengths emitted, it shows one kind of the shining, and to that we say lustrous behavior, and that shining you can say as a reflectivity for that particular metal. So reflectivity point as such in detail I had not discussed, only color observation I had discussed. But now I am going to narrate, or I am going to stress that point. Reflectivity is a lustrous property of metal, and that lustrous property is due to quasi-status continuum of various orbitals in metal. Means what? Untiming understand is one kind of theory called as band theory, a extensive portion of molecular orbital theory. So as per band theory applied to the metal, there remains a various energy levels, very closely spaced energy levels, and through that closely spaced energy levels electron can excite and can return also. And during returning here, one kind of shining we come across, one kind of luster we come across. We say it as a reflectivity. So is that point clear, which was not covered till now? Lustrous and reflectivity.
Yes, sir.
Yes, sir.
Okay, good. Next point is surface coating. This point also was not covered, but it is one kind of application of the these transition series metals, you can say, or the metals. See, while preparing ornaments, a gold ornament, silver ornament, we say the water of gold, water of silver is given to that. Means it's not a perfect silver, it is not a perfect gold, or even a vehicle, you say in vehicle, if metallic rim remains, metallic region remains, or metallic spokes remain, then those metallic part is coated, is covered by zinc or chromium or other. See, silver, gold are costly, so we come to the other elements coating, other metals coating. So metals coating, a layer of metal also can be established, and it is because of the positive charge carried by these metal ions, electropositivity beared by these metal ions, and that electropositive will help us to fix them as like sticker, glue, or fevicol. You take a fevicol, and with the help of fevicol you can stick a paper like a sticker. But in case of these metal ions or metals, where is a sticker, where is a fevicol? That fevicol is in the electrochemistry, electrochemical arrangement, electrochemical understanding. So positively charged metal ions, say the zinc metal ion, that zinc metal ion will be attracted towards a plate which will be negatively charged, and that attraction will be so huge and fixing will be so perfect that zinc will later take that electron from that and will become Zn plus 2. Ion will become zinc, and that will be plated, that will be coated on that, maybe a steel material or iron material or any other material. So we can coat one metal on the other metal. So that coating portion was also not explained. That coating portion is related to one color also, and that portion related to reflectivity also, that portion related to corrosion. Corrosion means where there is a loss for the metal or deterioration of the metal. So there surface coatings, and the surface coating we find what the colors. Yes, students, are you following what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. And about the particle size, maybe shortly I told to you, gold, generally we say color of gold is golden or yellow. I think you only have answered. But I told you gold can be blue in color, gold can be red in color, and that color depends upon particle size. So what is the general explanation till now are given, okay, because of transition, that basic is certainly there, but that basic, that energy levels changes if particle size changes. If energy level changes, then the wavelength absorbed will change, or wavelength emitted will change, and because of that, absorbed color or emitted color will be different, and that magic is possible by means of particle size. Is that particle size point also clear? Because I told, I think one time, gold is gold but can show the other color. Is it clear?
Yes, sir.
Yeah. Now see next point. Packing density for metals. That point I had not covered here. But in semester 3, we have discussed structures of solids. Their packing density calculation also were not done, but FCC, BCC, or simple cubic, like a different arrangement do remain. Are you understanding what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
So metals are packed as like we pack mangoes in a box arrangement. So accordingly, of course, size of the mango depends. The on which the number of the mangoes will depend. Or arrangement how we do accordingly also number of mangoes packed in the box will vary. I like we can pack the mango box. Nature packs metal box. Means metals in nature are with packing, and their packing, if there, then efficiency of packing we can find, and that is understood by terms of packing density. So for metal, suppose if it is with less packing density, say simple cubic or BCC, we can easily cut that metal. But strong packing density, FCC or HCP, it is not easy to cut that metal. So behavior of the metal depends upon packing density. That point I had not covered, and I'm not covering also in detail because next year we are studying it in what the detail. Here just for information, that point is mentioned. What is information you are getting from that point? Metals are packed in nature with different arrangement, maybe simple cubic, maybe body centered cubic, maybe face centered cubic, or hexagonal cubic arrangement, or hexagonal closed packing. Is it clear?
Yes, sir.
Yes.
Okay. Next point is nature of d orbitals. Five d orbitals are there. Names also I told to you. Yes, which d orbitals are there? Will anybody help me? At the time you might have not paid attention because I said just listen, like what I said. Yes, d orbitals which act like for p means p sublevel. Three p orbitals are there. Which are those? Px, py, and pz. Likewise, for d, which orbitals are there? D is a sublevel.
DXY,
Right, dxy. Next.
YZ,
Yes.
XZ.
Yes, right. dxy, dyj, dxz, these three are non-axial orbitals. Listen now, timing only. Non-axial. And further two are there, dx square minus y square and dz square. Those are axial orbitals. So those d orbitals. And color of the compound will depend upon number of electrons in d orbitals. And electrons are there or not. What is the geometry of that compound? Tetrahedral, then it will show the more intense color. The reason and this point in detail you are discussing in the next year topic. But just should know that number of electrons or number of unpaired electrons on which color depends. Geometry of the complex on which color depends. And charge transfer transition, example potassium permanganate or iron thiocyanato complex. So wherever charge transfer transitions are there, their intense colors or intense absorption or intense emission is observed. So not only DD but charge transfer transitions are possible. That only you should know. Therefore, that point is included because if you see the syllabus is only for 9 lectures and wordings, if you see, is more. So wording is only for just introduction. Detailed studies are there next year. So is this point 2.1.3 clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Now let us revise 2.1.4 magnetic properties of transition metal compounds. Actually, I told you magnetic compounds or magnetic substances are of three types. What are those three types?
Diamagnetic,
Right, diamagnetic,
Paramagnetic.
paramagnetic,
Paramagnetic.
and last,
ferromagnetic.
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 right. Diamagnetic materials are repelled from magnetic field. Paramagnetic weakly attracted, ferromagnetic strongly attracted. Reasons for that. With examples, I told those types of the compounds, magnetic compounds. What is the reason for magnetism? Why compounds are magnetic? Let them diamagnetic or paramagnetic or ferromagnetic. Why are they magnetic? Compounds are magnetic or magnetism is due to dash.
Motion of the electron.
Okay, motion of electron is the additional description you have given, but I want simple answer. It is because of
Excitation,
No excitation. Motion of electron, the next answer. Before that, simple answer. It is because of who is a tiny magnet.
Unpaired electron.
Okay, yeah, let there be unpaired or paired, but magnetism is due to electron. If unpaired electron remains, then it will be paramagnetic or ferromagnetic. But if it is not, then we say diamagnetic. And diamagnetism is due to countering of magnetism. One electron with plus of spin will be with one magnetic moment, other electron with minus of spin will be with other magnetic moment in opposite direction, equal and opposite direction. Because of that, they will cancel, and therefore net magnetic moment will be zero. Mu will be zero, and to that compound or substance we say it is diamagnetic in nature. Students, are you understanding what I'm saying? You have given answer, you know this concept, I know. Yeah, are you getting what I'm saying?
Yes, sir.
Yes, sir.
Okay, good. So you said because of the motion of the electron, spin motion and orbital motion, those two kinds of motions are possible for the electron. So origin of magnetism, which is due to spin and orbital motion, that you have answered. And we are talking about motion or we are talking about speed because of one law. What was that law? One scientist conducted his
Faraday's
experiment.
law.
Right, Faraday's idea brought us to conclude electrons have motions, electrons have speeds, then why can't they contribute for magnetism? Interesting concept. Okay, but out of that, we think about the spin only this year. Equation for spin only and spin orbital magnetism in terms of Bohr magnet, but spin orbital magnetism we are understanding, but mathematical expression we are not. I'm giving, I had given already mathematical expression for spin only. Yes, what is the spin only formula to calculate mu, to calculate magnetic moment mu?
Square root of n into n plus 2.
Right, square root of n into n plus 2 Bohr magnet. What is n?
Number of unpaired electrons.
Yes, number of unpaired electrons. Okay, and what is the unit for that? Right, Bohr's magneton. Now I'm writing here one rule, one formula. This formula I had not given, but the little idea about this coupling I had given to you. And one law also you have concluded. We just had given a hint. One diagram was drawn, and you told me because of that law we can find a resultant vector. When spin vector and orbital vector come together, they form one angle. Then by completing that one geometrical entity and finding the diagonal of that, we get the resultant value, resultant constant, resultant coupling constant or coupling parameter. Yes, will anybody help me? Which law is there? Law of, yes, yesterday only you answered. Right, law of parallelogram with which we can find this value of j, and j plus 1 we can of course find out. So that resultant vector will decide, that coupling constant will decide the magnetic moment. Here magnetic moment depends upon both spin motion as well as orbital motion. You can say L. So this point, this formula only I had not mentioned, but I told you that resultant vector we can find out and magnetism we can determine. So it is in the syllabus. So just I now told you that's a spin only formula and spin orbital formula. For what? Magnetism, to measure in Bohr magnetons. They specifically said derivation not expected. Then which formula we apply for transition series element? Just you said mu is equal to square root of n into n plus 2 Bohr magneton. What is the name of that formula? Spin only or spin orbital formula?
Spin only.
Spin only. It means we are not counting or considering orbital motion. Means orbital motion contribution we are not calculating. So what we say for that? Orbital motion is, orbital
Disturb.
motion is disturb or
Quench.
right, quench. So quenching is one concept. Quenching of orbital moment. And that quenching means somebody answered just now. What is that? Disturbance. Then who disturbs the orbital motion? Who forbids the orbital motion? Who obstacles the orbital motion?
Unpaired electrons.
No, because of unpaired electron, we have those motions. But out of the spin and orbital motion is quenched, disturbed. Because of what? Who disturbs? Right, external magnetic field in true sense. So, but what I said, because of surrounding this orbital motion, orbital moment can be quenched, can be disturbed. So, surrounding may be solution, surrounding may be ligands. So, though that surrounding remain with the magnetic field, magnetic moment, and that cancels this orbital motion, that quenches, that disturbs. So generally we say, just I said, because of surrounding, this orbital motion is quenched. But to get disturbed, one speciality is there in transition metal ions. Only for them it is disturbed. Only for them orbital moment is disturbed. For lanthanoids or actinoids, that orbital momentum is not disturbed. So what is the specialty of transition series metals? On the basis of electronic configuration, you will understand why those electrons are quenched because of surrounding. Why surrounding disturbs only for transition metals but not for inner transition metals? Students could able to understand my question.
Unpaired electron.
The orbital.
Okay, unpaired electrons are there. Unpaired electrons are there in lanthanides also, and they are in transition metals also. But for transition metals only, that outermost electronic configuration or the orbital moment is disturbed. Why?
Due to the orbital.
Yes, due to d orbital. But what is the specialty of the d orbital? What is the specialty of d orbital? That specialty is not in f orbital, or that criteria is not there in f orbitals. Okay, I told no disturbances will be, if you remain in corridor, then the surrounding can disturb. But if you go deep inside the house, disturbance will be less. Surrounding disturbance, outside disturbance, I am saying. So for d orbital, the disturbance is more. But for f orbital, the disturbance is not there. Now, I'll give a hint to you. I want answer from you. Why d orbitals are quenched? Why electrons in d orbitals are disturbed? Because of surrounding. Yes, it's true. But why can surrounding disturb that d electrons, not f electrons? Because d orbitals are, yes, dash. Yes. Are you following my question?
Yes, sir.
Yes. Only
Yes.
complete one word. D orbitals are dash. I'll give an example. Corridor and inner room. D orbitals are dash. Let you take any metal ion where electrons will be there in d orbital, electron will not be there in 4s orbital. See, if you talk about the first transition series, metal ions I'm saying, electrons will be there in d orbital, but not in the s orbital. So because of that, what happens? That d orbital becomes, though it is n minus 1 d orbital, that d orbital becomes dash.
Completely filled.
No, not always. Not always. Because of removal of electron from 4s orbital, electron from 3D may be removed or may not be removed in that particular metal ion. But because of removal of electrons from 4s orbital, now d orbital becomes dash.
Ligands.
No, no. Metal ion, I'm talking about metal ion. Metal ion is with electrons in d orbitals and s orbitals. But you said you know that minimum oxidation state means number of electrons in s orbital. So those electrons are removed. Let you take scandium plus 2, let you take copper plus 1, let you take Fe plus 2 or Fe plus 3 or Mn plus 7. Any metal ion you take, you will find electron from 4s are removed. They are not there in ionic state. Only electrons, if are there, they are in d orbital. They are in, say, in first transition series elements, they are in 3d orbital. So because of removal of those electrons from 4s, now 3d orbital becomes dash.
Same energy.
Same as,
Is
no,
extra stability.
no, no,
Equivalency.
no. 3d orbital becomes, the first letter is O. 3d orbital becomes, example, see, just for understanding purpose, a skin remains. Skin is a coating. If you remove that coating, then whichever inner portion that we say becomes dash. At least you complete now. Because of removal of electrons
Outermost.
in 4s orbital, the d orbital becomes now.
Outermost.
Right, it become outer orbital. So those d orbitals are easily exposed. Those d electrons are easily exposed. Those electrons can easily interact with whom? With surrounding. And because of that interaction, there is a quenching, there is a disturbance, and that is there in transition metals. It is not in inner transition metals, that is not in lanthanoids, because in lanthanoids, whichever the characteristic electrons are there, they are in pre-penultimate f orbital, inner f orbital, inner room is used. So even after removal of the outer electron, say s orbital electron, still they remain inner, and because of their innerness, disturbance they don't experience, quenching they don't experience, but transition series elements or metal ions can experience quenching. Electrons present in d orbital can experience quenching. Therefore, we do not consider orbital moment contribution. So, what is the reason for quenching? That's the point in your syllabus. What is the reason for quenching? The d orbitals in which characteristic electrons are there in transition metals, they become outer orbitals in ionic state because of their outerness. Outerness, listen carefully, that word for which you have struggled a lot. Outerness. Because of their outerness, disturbance is easily possible. Quenching is very easy. Obstacle is very easy, and therefore we do not consider orbital moment contribution while calculating magnetic moment for transition series metals. Students, are you following what I'm saying?
Yes, sir.
Yes, sir.
Yes, sir.
See. Yes, so in these all lectures, whatever we have covered in this year, means this in semester and in this year, that we have revised it also. Now, remaining portion is there. Fastly, I complete the sense what I just informed about the chemistry of titanium and vanadium. It is also the memory base. You can work on that. This aspect, you can prepare the notes. And this qualitative tests of transition metal ions, general test for say chromium, manganese, iron, cobalt, and nickel, and copper is a very important from competitive exam point of view or application of chemistry point of view. But you will prepare for this 2.1.5 and 2.1.6. Yes, students, are you getting this point?
Yes, sir.
Yes,
Assignments I'll give
Yes,
later
sir.
on. So in this period now from tomorrow, there's a winter holidays are there. So in those winter holidays, you will work for these notes so that in that paper one, that's a 2.1 comparative chemistry of transition metals, a major lecture, 9 lecture syllabus we can what cover. Next year we can start what the next topic, next unit. But assignment I'll give next year only, but you can prepare meanwhile. This every portion you go through the syllabus and see whether you are with the notes or not. Is it clear to you what I'm saying?
yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, good, good. All you are the brilliant.
Yes, sir.
Yes, yes, very good, very good. All you are the sincere and enthusiastic to learn. It's a very important criteria for student. Okay, so you work for that in these few days so that you also will feel you have learned the chemistry. So next year means after few days only, we will complete the remaining portion. We will revise. And if in doubts are there, as usual, you are free to ask. So students, can we stop now?
Yes, sir.
Yes, sir.
Only two replies. Okay, others are replying in text box.
Yes, sir.
Okay, Shivam replied. Okay. Okay, fine, students. I stop my discussion now and I declare here today's session is over.